Up to now, we have been programming using a sequence of linear commands. Next, in this video, we're going to look at how we can introduce decision making into our programming. We will do this by using conditionals and loops. These features enable us to exploit the key strength of computers, their ability to repeat calculations and commands billions of times per second. Hence, fast analysis of big data and solving complex numerical problems becomes possible. Asking a computer to make decisions using conditionals and loops brings great power and complexity to your programming. Decisions are made in computers using true-false logic. We have already come across these true and false logic data types earlier in our course, and we refer to these as Boolean data types. We also have Boolean operators or logical operators. For example, we have identity operators to compare two variables and to check whether they're equal or not equal. We also have comparison operators, which check if variables are greater, less than, or greater or equal to, or less than or equal to. We also have an identity operator is, and is equivalent to is it equal to, and there is also a not equal to identity operator called is not. Finally, we have a membership operator in. Is B in the list 2, 3, 4, for example? Or is B not in that list? By comparing values of different variables using these conditional operators, computers and our programs can start making decisions. However, when we learn to combine these different conditional statements, we can create much more elaborate decision processes. We can do this by introducing Boolean algebra, which is built on the operators and, or, and not. These three basic operators can enable us to join up conditional statements together into longer logical sentences. The Boolean AND operator enables us to check whether two statements are true, while the OR operator enables us to check if either statement is true. Finally, the NOT operator inverts the condition of one statement. If, for example, in this condition A equal to B is true, NOT will invert it and we will get false. Using these Boolean operators, we can join together individual conditions to make a longer decision process. For example, we can check is the value of A in this short list, and is A less than or equal to B, and is B less than or equal to C, or is C not greater or equal to A. Like normal mathematical algebra, Boolean algebra also has a system of precedence for its operators. The combined precedence has powers, multiplication, division, addition and subtraction coming before the conditional operators for identity and comparison. And finally, the Boolean operators and or not having the least precedence in calculations. We can look at an example here and indicate the precedence using some brackets. Similar to mathematical equations, logical equations will have precedence to determine which operations comes first. The mathematical operation has higher precedence, such as multiplication, followed by division, and after multiplication and division, the conditional operators take precedence, such as greater than C, the membership operator not in, and finally the logical operator OR. All of this is very abstract, so let's look at some practical examples. Here in this notebook, I have defined some values of the variables A, B, C, and D, where D is a list. The first conditional operators we can try out are the identity operators. Is A equal to B? And no, it's false. Is A not equal to B? Will of course be true. We can also look at the other identity operators. A is B, which again will be false. A is not B, which of course will be true. The logical operator not, of course, inverts the condition of A not equal to B, so that comes out to be false. We can start combining some basic conditional logic using the AND operator. So here we'll require A to be less than or equal to B and B to be less than or equal to C to be true. And in this case it is. Next, let's look at a membership operator, starting with B in D. B is 2 and D has a value 2, so that is true. A is 1, and of course this is false. D does not contain a value of 1. We can look at the membership operator, A not in D, and A of course is 1, and D does not contain a value of 1, so that comes to be true. Another example using joined up logical operators is A less than or equal to B, or is C in D, and since A is less than B, the answer is true. Our goal here is to experiment with different conditionals and different combinations, and this is key, especially when you start to encounter such logical algebra. It's really important to play around with the syntax of these operators in order to develop a deeper intuitive understanding. After a while, you'll start reading this logical algebra as you do basic mathematics. And of course, you can combine basic mathematics with the Boolean algebra. And in those examples, you need to check the precedence of the operations to make sure that they occur in the correct order. In this example, we can see that the multiplication will occur first. Next, it will be division. Then it will be the comparative operator greater than, followed by not in, and finally or. Our first application of the simple conditionals is the if statement. And the if statement enables us to make decisions based upon some condition. If the condition is true, then we can perform some commands or actions. For example, if we ask a user for their age, we can have an if statement to print something to screen depending on how old they are. In this case, the condition is greater than 25. The colon symbol then implies that this is an if statement, and the next line will be automatically indented. We can add a list of actions that are all indented after the colon symbol. In this case, it's a simple print statement to say a phrase. Next, we can also add an else decision. If else means that if the first condition isn't met, else do something. So if the user is less than 25, we print out an alternative message to screen. In this case, the else command is in line with the if, there's no indentation, and it ends again in a colon symbol. We can build even more complexity into these decisions by adding else if. For example, we can specify an age bracket between 25 and 30 using the AND operator. Else if age is between 30 and 40, we can print something else. And again, we can keep adding more and more else if lines to specify different conditions, such as between 40 and 60, 60 and 70, and beyond 70. The final else line is our default line. So to summarize, we can use an if to start a conditional statement. We can then build up a collection of additional tests using the else if, and finally provide some default answer. If none of the previous conditions are reached, we can use an else. The next type of loop we'll look at is called the for loop. And for loops are very, very powerful because they enable us to reiterate, that is to repeat, actions a certain number of times. And it enables us to automate many long calculations or other types of processes. The for loop is defined again using a simple syntax. In this case, it's for a variable in some list, do a command or a sequence of commands. In this case, the variable is count, and for count in some list, do something. So the for loop iterates through that list, so count will have a value of 0, 1, and then 2. And the simple command we're using here is printing count squared. So the output of this simple for loop will be 0, 1, and 4. Formally, we are using a list to reiterate the loop, and this can be defined in a general type of syntax by some variable in a list execute some sequence of commands, i.e. command 1, 2, all the way to some end command. The list can be created by the function range, and range, as we've seen previously, creates a list of integers, in this case from 0 to 2, or indeed you can use any one-dimensional sequence of numbers, which you can create also using NumPy's linspace or NumPy's arrange, for example. With the basic built-in range function, you can also specify the step, and this is when you provide 3 arguments to the range function with a starting point, a stop point, and a step size. Again, you can have a sequence of commands as long as you want. Just bear in mind to keep your loop efficient. The more commands you have, the longer it will take to execute the calculations. With the case of range, the step size can only be an integer. If you want a step size that's a float, you can of course use NumPy's arrange function. For example, we can have a for loop that has a starting point, a stop point, and some non-integer step using arrange. You can build together loops such as for loops within each other, and this is referred to as creating nested loops. A very simple example is to have 2 loops nested within each other. In this example, we have x being changed at each step in the loop from 0, 1, 2, and nested within that loop there is a loop to increment the value of y from 0, 1, 2 as well. Notice also that the nested loop is indented 1 full indent over to the right. So as you add more and more loops in a nested environment, they get progressively more and more indented towards the right hand side. Let's look at an example where we're calculating the Rydberg formula using a nested loop. In the Rydberg formula, we can calculate the emission wavelength for a simple hydrogen atom, starting at an initial state Ni and finishing at Nf. And the difference, of course, between the two states is emitted as a photon of energy. Our first for loop will be to loop over the final energy states, and that's from 1, 2, 3, and 4. As you can see in the diagram above, the bracket series all finish at 4. So that's the lowest final energy state that we will calculate with. We'll print this out, and we want to then have a nested for loop that increments through the initial energy states, starting at an energy state of Nf plus 1, finishing at Nf plus 7. So the initial energy states can range from n equal to 2 to n equal to nf plus 7. So we will calculate 6 different transitions for each final energy state. The 1 over lambda we'll calculate using the equation shown, and then we'll convert that to nanometers and print out the wavelength to screen. So we're going to print out for each transition, for each line in that diagram, we'll print out the wavelength in nanometers. So very quickly we can see for each final energy state we've got a sequence of 6 different transitions, and those 6 wavelengths correspond to, of course, for the Balmer series, for visible light, and as we go to longer wavelengths we go towards the infrared. So after that simple example of nested loops, we'll move on to looking at while loops. And while loops enable us to keep repeating a list of actions or commands until a certain condition is reached. In this very simple example, we will have a while loop that will calculate the sine of I over 100 so long as I is less than 100. So at each step in the loop we increment I plus 1, and after 99 iterations of the loop will stop. Let's look at a more relevant example to physics in the case of modeling the free fall of a skydiver. And in this case we'll have a while loop that will keep calculating the position and speed of the skydiver so long as he doesn't reach the ground. So until the height is equal to 0. So we're going to calculate numerically the time to arrive to the ground, and at the end of this we can calculate the velocity. So when we calculate something numerically, we're going to break down the problem to very small time steps, in this case 0.01 of a second, and our while loop syntax will look like this. While y is greater than 0, i.e. while we're still above the ground, update time and update the velocity and then the position. When the position reaches 0, the skydiver hits the ground, and then we can simply calculate and print off the current time and velocity. Let's look at this in more detail by writing the simple program to calculate the velocity and the free fall time to the ground. First, we'll add an initial comment to the top of our code to describe what we intend to do, and we're going to calculate the terminal velocity and the impact time. Our first code is to load the modules we'll need. This includes numerical Python and matplotlib, which we'll use later on to visualize the change of position and velocity with time. The key constant we need is the gravitational acceleration. Next, we will initialize our while loop, and here we need the initial velocity, which is 0. The initial height is 5,500 meters. The initial time is 0, and we're going to simulate this for 100 seconds with a time step of 10 milliseconds. So we initialize our variables next. So we set time, position, and velocity to their initial values. Once they're initialized, we can start the while loop. And the while loop here is to specify that as long as height is above the ground, i.e. above 0, update the new time, so it'll be time 0 plus dt and so forth, and then update the new velocity, where that will change by acceleration multiplied by dt, the time step. And accordingly we can update the position where the skydiver is falling from a great height, and that will decrease at each time step by velocity multiplied by dt. So initially we can already see that we have a fall time of the order of 30 seconds. Next we can also print the final velocity to screen by simply printing v. And of course, we can add the necessary units to describe these quantities. So the time to reach the ground is 33.5 seconds, and the final velocity at that point is 329 meters per second. In this example, we haven't saved the data as a function of time. We've overwritten the variables t, v, and y at each step in time. In the next example, I want to show you how you can create arrays which you can populate with the values at each instance in time. So we'll have an array of time, velocity, and y containing all of the different values at each time step. To do so, we have to initialize the loop with the arrays, and the arrays are initialized here using numpy zeros, where we have 3 different arrays populated with just zeros. And the important thing is that each array for time, position, and velocity has n values in it, and we're going to fill those n values as we go forward in time. So the initial values for t, y, and v are the same as before. We want a loop counter in this case, and we're going to call it I, and I is initially 0. And we will then have I incrementing at each time step, and we will use I as the index value in the arrays. So at each time step, we will have t of I is equal to the previous time step plus the change, and the same for the velocity. So I minus 1, it will be the previous time step, and we're just adding on the little difference each time, incrementing velocity and position. At the end of the while loop, we'll have 3 complete arrays containing all of the data for time, velocity, and position, and then we can start to visualize that data. But first, we have to solve 1 or 2 little bugs. And the first bug here is v contains a sequence, or it's an array, so we have to make sure it's v index I. And next, we have an issue with the value of n. N needs to be an integer. It's an integer number of time steps, and in our calculation of n, we have to make sure that the brackets surround the full calculation. So the time difference divided by the time step will give us a number of time steps, and we have to make that an integer. So once that's corrected, we now know that our code is working. We get the same answer as before, but this time we've got the data stored in those arrays. And now we can either save that data to file, or we can visualize it using some graphs. So we can plot the time on the x-axis, and on the y-axis we can look at position in this case. You'll see here that I'm taking the position using the slice 0 to I, just to ensure that both t and y have the same number of data points. So we're going to visualize the position and the velocity as a function of time. Since we're falling downwards, our velocity will be negative, so we can also just visualize the absolute value of velocity using numpy's absolute function. So we see a velocity increasing from 0 to over 300 meters per second. And of course, remember, this is in the absence of air. Air will make a very significant difference to our model, and it's useful to look at an example where we can include air and include the resistance or the drag from the friction of falling through a dense medium. In the case of drag, we'll have an extra term in our model, the plus Fd, this drag force, pushing up against the skydiver and impeding his motion towards the ground. The effect of drag you can model very easily by defining some cross-section for the skydiver, having some length and width, assuming he's falling in a face down position. The density of the air and the mass of the skydiver, together with the coefficient of drag for the skydiver's body, are all the ingredients we need to include drag. So again, we're going to calculate numerically the time it takes until he meets the ground and the terminal velocity. And this will be very interesting to see if it's different at all or if it's significantly different to the previous example where air resistance wasn't included. Now, you're going to try this yourselves later in the course, where you're going to adapt the previous simple code to include a changing acceleration. As you see from the mathematics, our acceleration will no longer be simply minus 9.81. There's also a change in acceleration due to the air resistance. Finally, let's look at the concept of infinite loops. Infinite loops can be either intentionally created or they can be an accident. And in the latter case, they can be somewhat of an annoyance that you're going to encounter at least once when you start writing code for these for and while loops. An intentional infinite loop is something we want to run continuously without a pre-specified cutoff. We're going to, in this case, run it all the time. So using this true statement, the while loop will continue to run indefinitely. Now, because it's intentional, we've included a break statement, and the break statement will come into effect if something occurs. We will stop the loop. Now, in this example, we're asking for the user prompt of a name or to type a keyword quit. Now, if quit is typed, the break function is used and the loop stops. So this is a simple intentional example of an infinite loop. The unintentional example is shown here. In this case, we've made an error in writing the code and the loop will continue forever. And it's important to know how to stop these annoying cases of infinite loops. You can quickly see here that the error we've made is not incrementing time but multiplying it by 1. Therefore, time will never increase and it will never be greater than 10, which is the initial logic in defining the for loop. Therefore, it's very important to know in advance how you can stop infinite loops. And typically this requires a user intervention. Depending on which way you like to code, this will change. So for example, if you like to program using a Jupyter notebook, you can click the kernel stop button to interrupt it. If you're working in the Python interpreter, you can press the keys Ctrl+C on your keyboard and that will stop the process. Alternatively, if you're running a script from a command terminal, you need to press Ctrl+Z.